Okay, this is the first video for Outcome 2 at BBCHS. This is Pre-AP Biology. We will be talking about populations. And as we go through this unit, we need to think about why we would want to know how many individuals are in a population, whether we're talking about humans or in Bourbonnais or dandelions at Perry Farm or bacteria in a culture plate. So you should have some student notes out and go ahead and fill these out as you go along. So hopefully you've watched the video about the Australian mice explosion. The mice were not actually exploding, but their population was. Some questions following that video for you are, first of all, why do you think the mice populations exploded like they did in Australia? So think about that for a little bit, write some thoughts down. And what will eventually happen to this population of mice? Again, if you haven't watched the video, go back and do that right now, because otherwise a lot of this won't make sense. So a population is the number of organisms of a particular species, just one species, that live in one place at one time. Okay, so we talk about the human population or dandelion population because those are one species. The population density is the number of individuals in a population per unit habitat area. So when we talk about a density, we want to know if that is in a square mile or a square meter or 10,000 square meters. Okay, so we want to know how overcrowded is it in that area. Can you think of an example of an animal that lives at a low population density? Something that would require a lot of space and maybe only a few individuals per unit area. And then what's an example of an animal with a high population density? Okay, think about that. You've probably seen some, I don't know, I think about a low population density might be something like a lion or a tiger that requires a lot of area to move around. High population density, I think of those gnats that get in your face and will never leave. They live at a high population density. Okay, so once we know what a population is, we can talk about their dispersion. How are they distributed? How are they dispersed in nature? We have three different examples here that we're going to talk about. So the uniform dispersion is, as shown here, it's pretty uniform. They're all spread out pretty equally. And this is pretty common in organisms that defend their territory, like wolves or spiders. The middle one is called random dispersion. It is kind of random. So dandelions, for example, will disperse as the wind blows, and they will set roots down wherever they are planted. So in this case, that's a really good example of random dispersion. There's no particular pattern there. Now, clumped dispersion is kind of interesting because these will often be clumped around an entry to a prairie dog hole, for example, or ants around an ant hill. They'll follow a clumped dispersion. Okay, so sometimes in ecology we want to know what kind of dispersion pattern is an organism following. How are they distributed? Okay. We also want to know how population growth is happening. There are several different ways that populations can grow and decline, and it follows this fairly simple equation. Okay, if you want to add the births, right? If you have some new animals being born, you add those to the numbers. If some immigrate or they enter the colony or the population, you add those numbers. If you have a death, you subtract it. The same thing with emigration, because emigration means leaving the population. So for an example, let's look at this word problem. There's a population of penguins at the beginning of the year with 150 individuals. If 45 were born, 30 died, 15 immigrated, came in and joined the colony, and then 4 left the colony. It seems pretty complicated, but the question is, what is the population density? I'm just actually going to be super nitpicky about this and cross out density because they said nothing about the area, did they? Okay, so we just want to know what is the population number, right, of the colony at the end of the year. Okay, but we did cross that out. You would do some simple math. Let's cross it out again for extra emphasis. Okay, and it's fun to use the stylus. All right, so we started off with 150. We added 45. That got us to 195. We subtracted 30 from that 195 and got to 165. 165 plus the 15 that immigrated gives us 180. And then if you subtract those 4 penguins that left the colony from the 180, you end up with 176. Okay, simple enough. Let's exit the drawing. Go. All right, so now population growth will often follow this logistic growth curve. This is also known as the S-curve because it's shaped like an S. And it starts off somewhat slow, but at some point we reach this exponential growth phase where growth looks like it's going up exponentially, right, without any control. But because we are because we're in natural ecosystems and there are things that slow down our growth, at some point the population growth levels out like this. And the point at which it levels out is kind of called the carrying capacity. Okay, so think about what that carrying capacity might indicate. This is represented by a letter K. This is a little bit beyond what you need to know for this class, but it's kind of interesting, so follow along. The carrying capacity is the maximum population, right? What is the highest number of individuals in that population that an ecosystem can support without harming the environment? Okay, this fishbowl on the left has surpassed its carrying capacity, right? They're going to be harming the environment in a big way. The one on the right may have met its carrying capacity, and 3 to a fishbowl might be as many fish as this fishbowl can carry. Okay, so the carrying capacity here would be 3 goldfish. So apply that to the situation in Australia. What will likely happen to the mice in Australia? At the time of the video, the population growth was showing exponential growth and the farmers were pretty frustrated, but they were also kind of anticipating that carrying capacity was going to be met. So see if you can jot down some thoughts about that in your notes. Now, how the carrying capacity is determined is through these limiting factors. Okay, now limiting factors are pressures that restrain the exponential growth of populations. Pressures that kind of put a cap on it, right? Put a cap on exponential growth of populations. Another way to say this is that limiting factors are things that can kill you, right? So we have several different types of limiting factors, and we're going to introduce them here. One is a density-dependent limiting factor. And this is when population density, so how overcrowded you are, or not overcrowded, how this impacts population size. These tend to be biotic factors, and I think once you see the examples, you'll understand a little better about why these are density dependent. Okay, so in the Australian mice explosion, there were several density dependent factors that mice were experiencing, and these limiting factors were stronger. They were better able to kill the mice because the mice were at a very high population density. And what I mean is this, okay? Disease is a density-dependent limiting factor, okay? These tend to be biotic, right? Living limiting factors. Disease can spread through a mouse colony a lot more quickly if the mice are always in contact with each other and they're overcrowded, Okay? Intraspecific competition, that means competition amongst themselves, is going to be harsher. That's going to kill a lot more mice when there's a lot of them to compete with. Okay, so here's intraspecific competition between two turkey vultures. Intra means within, so within that same species, the mice are competing. Okay, and this could be competition within a population for food, water, space, mates, any of those things, anything that's going to be in limiting supply. And predation. Okay, this is also a biotic factor because it involves a predator. This is a density-dependent limiting factor. The mice are going to be, the predation is going to be a lot stronger, and it's going to bring in a lot more predators if the mouse colony is at a high population density. Okay? So in contrast to that, we have some density-independent limiting factors. These tend to be abiotic, and they are density-independent because they will wipe out a population or a good portion of the population, whether that population is small or large. Okay, so high density, low density, it doesn't matter to natural disasters, right? A flood will wipe out however many mice are in that ecosystem. Okay, same thing with lightning strikes. Human disturbances are density independent. We create pollution, we can cause loss of habitat. Well, it doesn't matter if 2 mice were in that habitat or 200 mice. If the habitat is gone or if the pollution causes air quality changes, then those mice cannot survive. Okay, and finally, as we learned in outcome 1, dramatic changes in temperature. Okay, in climate change caused by CO2 emissions and so many other things in the environment, these can be density independent limiting factors. And a lot of organisms, a lot of populations of organisms worldwide are suffering from this right now, as you learned. So I'm going to leave you with this question. What are some limiting factors that affect the human population? Remind yourself what a limiting factor is. This is going to come up time and time again, so make sure that you understand what a limiting factor is. And maybe jot some down that are density dependent and density independent.